Hello and welcome again to our channel. So this is the second part of the infinite square well, where I will discuss about the different types of the properties of the infinite square well. As in the first video, I have discussed about the derivation of this particular expression I have written on this board. That was the particular how to derive this particular expression and solving the Schrodinger wave equations for this expression and some of the basic concepts about the infinite square well. So in this video we are going deep about this infinite square well, where we discuss that what boundary conditions the wave function has to follow so that we can get the more general expression of this particular wave function of this particular infinite square well. So let's start our today's video of the second part of the infinite square well. So here you can see that I have made a visual explanation of the infinite square well. As you can see here that there is an well which is from x is equals to 0 to x is equals to a, and there is a wall, and inside the well the potential is 0, but outside the well there is the potential infinite, and this particular well is surrounded by the infinite potential, and that's why the particle inside this well is not capable of just escaping through this particular well. So now let's move to the more general solution to this particular explanation. तो मैंने पिछले वीडियो में एक्सप्लेन किया था कि हमारे वेव फंक्शन को ज़ीरो होना चाहिए हमारे इन्फिनिटी पे जब हमारा पोटेंशियल इनफाइनाइट हो, क्योंकि इनफाइनाइट पोटेंशियल पे हमारा वेव फंक्शन ज़ीरो होना चाहिए, क्योंकि अगर ज़ीरो नहीं होता इट मीन्स इट हैज सम प्रोबेबिलिटी ऑफ फाइंडिंग द पार्टिकल एट इन्फिनिटी विच इज़ नॉट ट्रू. That's why the wave function has to be 0 at infinity. It means, first of all, the criteria that wave function has to follow is that at x is equals to 0 and at x is equals to a, it has to 0. And this is the case that the wave function at 0 is equals to the wave function at a, and this quantity must be equals to the 0. So if this quantity must equals to the 0, let's derive some expression. So it means that psi, we can write it as psi 0 is equals to the a sine 0 plus b here plus b cos 0. So this is the condition that the wave function has to follow. So sine 0, this particular quantity a sine 0, so sine 0 is equals to 0, it means this first particular quantity becomes 0, but the cos 0 is equals to 1. So what we will get is that if psi 0 is equals to 0, it means 0 is equals to the b. It means b has to be 0. B has to be 0. So now in this particular equation, the equation in this particular box, we put the value of v as 0, and what we will left is our new equation. The new equation of the wave function for the infinite square well, which I'm going to write here, is that the wave function x is equals to the a sine kx, a sine kx. So this is now the particular form of the wave function in the infinite square well. Wave function is equals to a sine kx, because here the b becomes 0. So if the b becomes a 0, this particular whole equations become 0. So now this is the particular wave function. So this is the general expression of the wave function for the infinite square well. Not general, the form that we used after applying the boundary conditions. The general solution of the infinite square well we will discuss in the next video, which requires another detailed video of knowing the general solution as the linear combination of the separable solutions. So this requires a video. In this video we are only going to discuss some of the properties of these wave functions and then the general solution of this particular infinite square wave. So now we reduce this particular wave function equation, as this particular equation, which is psi as x is equals to a sine kx. Remember, this is time independent. Here this is not similar as wave function xt. These two quantities are very different from each other. So now if we just move down some another equations to this, what will happen is that after doing some more calculations, so now doing one more calculations, what we will get is that we have gonna apply the second boundary conditions for this particular wave function, that this particular wave function has to be 0 when it is at a. It means we can write it as psi a is equals to the a sine k a. So psi a must be 0 as I have written here to satisfy the boundary conditions for this wave function. So here you can see that there are two situations where this particular psi is 0. One situation is that this particular a constant is 0, or this particular expression ka, or you can say that this particular expression ka must be 0, because then sine 0 is equals to 1. So when this particular ka is 0, so I'm going to write here another thing, that when this particular ka is going to 0, this particular ka is going to 0 at 0. You can say that 0 or pi, and here you can see that 2 pi. Here you can now see that 3 pi. So this particular k is 0, because you know that sine 0 is 0, sine 180 is 0, sine 2 pi is 0, sine 3 pi is 0. So if this quantity is 0, then psi a is 0. It means ka must be 0 when the value of ka is 0, pi, 2 pi or 3 pi, whatever. So we can write this in a more general form as ka is equals to the n, where n refers to the principal quantum number. For now n is any integer, n pi, and now you can write this as k is equals to the n pi divided by the a, n pi divided by the a. Now what is the value of k here? So in this previous video I have determined the value of k, so I will write here the value of the k. So the value of k generally, as in the solution of this particular infinite square wave, I have told about you the particular k. So k is what equals to the root under, k is what equals to the root under 2 m e, where e refers to the energy, total energy, divided by the h cut square. So now squaring both sides, k square, and this particular explanation is square. So this particular explanation is square. What will do? So this will yield k is equals to the 2 me upon h cut square when we will do the k square. So squaring both sides, what will squaring both sides, what we all will get is that squaring both sides, what we all will get is k square is equals to the n square pi square and divided by the a square. Now we are putting down the value of the k square. Now here putting down the, oh sorry, here is the k square. So now putting down the value of the k square in this particular equation is that after putting down the value of k square, what we will get is 2me divided by the h cut square is equals is equals to the n square pi square divided by the a square. Now what's the equations for the energy? So just moved all this particular to the right hand side and leaving energy in the left hand side. What we will get is that energy is equals to the n square. Sorry, some mistake here. So here you can see that we can write that energy is equals to the n square pi square h cut square or h bar square reduced Planck constant and divided by 2ma square. So note down, this is the most important equations in the infinite square well, and this yields a very important value which I am going to just write here. That's how this is very good in the infinite square well and how it predicts some of the great things in the infinite square well. So this is the equation of energy for the infinite square well. So what does it predicts? It predicts that the particle inside the infinite square well can only have a certain energy, not an arbitrary energy. As you can see that here n should be 1, 2, 3 and 4, not 1.5 or whatever this is. So what this particular energy is predicting, that it can only have the discrete energy levels in the infinite square well. It cannot have any arbitrary energy levels. So this is the first thing of the infinite square well. First of all, we derive this expression. First of all, we put down all the boundary conditions, derive this equation, and after deriving equation, we derive the equation of energy in the infinite square well, which predicts that energy can only be discrete. Energy can only be discrete, not the continuous energy is here. Energy can only be discrete energy levels, as discrete energy levels also existed in the atoms, but here it is an infinite square well. And I have also told you that in the infinite square well and atoms both are equivalent things, both have the electric potential, but here the potential is infinite. So this can only be discrete energies, not an arbitrary energies. When you put down the value of 1, it is equals to the, or you can 0, 1, 2, 3, 4, whatever the particular value is. So we derive the expression of the energy for the infinite square well. So let's discuss a more general form of this particular expression by determining the constant a. I have said that wave function has to be normalized. It means its integration from negative to the positive infinity or whatever the limit is has to be 1. Now here this particular a constant is equals to, I am right here that this particular a constant is equals to the root under 2 by a. So now the final form of this wave function for the infinite square well, not final form, but the more general form that you find in every textbook is psi x is equals to the what a. So putting down the value of a as a root under 2 by a, which is a root under 2 divided by a, and sine. Now putting down the value of k. So what is k? So k is n pi upon a. So k is n pi upon k. So psi x is equals to, putting down the value of k as n pi divided by a into the x. So this is the particular equation for the infinite square well or the wave function of the infinite square well. So this is the more general expression. So we have derived the equation, putting down the boundary conditions, determine the energy levels. That energy levels is discrete in the infinite square well. This is a very important property you should remember, that there is a discrete energy levels, and I found this very interesting. And then the final form of this particular expression, psi x is equals to root under 2 by a sine n pi divided by a into x. So now we are going to discuss some of the properties of the infinite square well. Some of the interesting properties of the infinite square well we are gonna discuss here. So first of all, properties. First property is that is contains and discrete energy levels in infinite square well. Okay, so this contains discrete energy levels. So this is the first property. But now let's move to the more important properties, which is here as follows the particular thing. So before discussing about the properties of the infinite square well, I have a quick recap of some of the properties of the time independent Schrodinger wave equation, that it yields an infinite set of solutions. How? So let's see here the equation that you derived. Psi x, yeah, here the equation that you derived at psi x is equals to the, here is n, psi x is n x is equals to root 2 I say psi n pi x upon. It means if we put down the value of n is equals to 1, 2, 3, 4, 5, 6 and every time, it means this particular solution of this particular solution can have infinite set of solutions. It can have infinite set of solutions for every value of n. As I have said that n can be 0, 1, 2, 3, 4, 5, 6. So at every value of n, there exists an infinite sets of solution of this particular equation. So this is an important thing, that these particular Schrodinger equations remarks and various types of the solutions or the sets of solution in infinite set of solutions, you can say, for every value of n. For value of n is equals to 1, you can say that psi 1x. For 2, you can say that psi 2x. For 3, you can say psi 3x. And just like this, there exists an infinite set of values of this particular equation, infinite set of solutions, psi 1x, sine 2, sine 3, sine 4, until infinity it has a set of solutions for every value of n. For every value of n, there exists an infinite set of solutions of this particular time independent Schrodinger wave equations. And this has some very important remarkable properties. So first of all, the first property is that they are even and odd. It means if psi 1x is even, psi 2x odd, then sine 3x even. It means they are even odd, and even odd, and so on. Sorry, here it should be, sorry, here it should be odd, even, odd, even, odd, or you can say that it is just like this, that if the first is odd, even, then odd, then even. So this is the first property, that the wave function are odd, even, and odd, and even, odd, even, odd, and so on. It is shows the properties like this. So second, what's the second property of this particular wave function? So this particular is, so the second property is that they are orthonormal. The wave function, it means psi 1x and sine 2x are orthonormal in the sense that if we integrate it from a particular, say that if I integrate the expression from 0 to a, as in this case of this particular thing, 0 to a, sine, let's say sine 1, sine 1x into psi 2x dx is equals to the Kronecker delta, is equals to the canonical delta. They are orthonormal. It means if there is a one solution psi1, second solution psi2, third solution psi3, fourth solution psi4, they are orthonormal. They are orthonormal, and if we integrate it from 0 to a with respect to dx, it will give us the value what known as canonical delta. So canonical delta is nothing. The value of canonical delta depends upon these quantities, that if it has value, it can have value 0 and 1 respectively, depending upon their subscripts. If m is equals to n, there exists a value. If m is not equals to n, there exists a value between 0 and 1. So it means they all are orthonormal with each other. Like the x-axis, y-axis, and z-axis are orthonormal with each other. They are orthonormal with each other in a sense that if we integrate it from 0 to a, it will give us the value 0 and 1 depending upon their subscripts 1 and 2 respectively. So these are some of the remarkable properties of the infinite square well. So what we have discussed in this video is about some of the more general form of the infinite square well, that how we generally describe infinite square well, then what's about the general solutions, or you can say that the more defined way of the infinite square well, which is sine nx is equals to root under 2 by a sine n pi x divided by a. In the next video we will show you about any other solutions of the Schrodinger wave equations from different potentials. Like this is a potential, for different potential, maybe for the free particle whose potential is 0, and for the harmonic oscillator, and for different things. For harmonic oscillator we define the potentials. In the quantum mechanics we will solve this particular explanations. So this is a video of mine where I have discussed about the more general form of the infinite square well, its energy derivation, its remarkable properties, that it yields an infinite set of solutions for each individual n. So this is a video of mine of the infinite square well. So if you have any doubt related to this particular infinite square well, you can comment down the doubts so that I know about what you have not understand in this particular video. So thank you for watching my video for this topic, infinite square well.